Okay. Hi, everyone. So this is Group 12 presenting our project, Understanding Human Emotions the DistilBERT-CNN way. So first to start off, let's introduce ourselves. So I'm Chelsea Salyards.
Hi, I'm Manas Ranjan Sahu.
Yep. And so before we get into the meat of the presentation, you can go back to the previous slide, actually. So I just want to tell a little bit of an anecdote, um, really a personal story about how the sort of research our project covers has benefited me. So, like many people out there, I have seen mental health professionals, and throughout my life, I've talked to a lot of different therapists. But for me personally, talking to a human therapist can be difficult, and it's an experience that only ends up harder because humans are fallible. And even when trying their best, therapists, as people, can say the wrong thing. So for me, I suffer a lot of social anxiety. And although therapists are trained to be neutral on issues that can cause controversy, like cultural, religious, or societal issues, inevitably their internal biases come out. And I have struggled to feel safe, especially in such a vulnerable environment like therapy. So, a while back, I tried talking to an AI chatbot about some problems, and I was actually really impressed both by how it responded and how I personally reacted to it. So, the chatbot itself did a really good job of using therapist appropriate languages and responses, and I personally felt a lot more comfortable with it because I knew it wasn't an actual person who had opinions, and it didn't matter if it believed me, it couldn't believe me. And it's also the aspect of if there were any appropriate responses, which there weren't, I would have been able to laugh it off more easily because it wasn't a human saying it. So, all of that to say, and you can go ahead to the next slide now. So, AI functionality like this, the functionality where an AI can respond to emotion in the data it receives, like written text, for instance, that's all part of sentiment analysis. And sentiment analysis involves in determining the emotional tone behind the data. And not only is it important for applications like AI therapy, like I mentioned, it's just important. It's crucial for modern AI to function in general. So, other applications where sentiment analysis comes into play are chatbots in general, not just AI therapists, because it needs to get the emotional tone in order to respond to the users correctly. And it can also be used in more dedicated applications like auto filtering social media content for harmful language, harmful content, and it can be used to figure out what recommendations it should suggest to end users. Plus, by making AI responses more human-like and empathetic, this increases further adoption in its use and increases its overall user base. And like in very recent news, you can see a lot of this right now with the backlash to the release of ChatGPT 5. So apparently, the newly released model is a lot less empathetic in tone to ChatGPT 4. So people aren't very happy about that. So you can go to the next slide.
All right. So yeah, I mean, we all discussed about why sentiment analysis is important. Now, let's try to also understand that as we have had decades of research in AI, why exactly we haven't able to grasp the nuances of sentiment analysis. Now, when we look at the way people talk, our conversation has been developed over centuries of different language modifications. And nuances like sarcasm and irony are something that AI models have yet to grasp. Like if I say, "Hey, that's a brilliant idea," you would not be able to understand if I meant it as a compliment or if I was being sarcastic about it. If I just say that's just great, I could mean that yeah, that's actually great, or that's just great that I'm in such a soup right now. There could be other cultural and linguistic differences as well. Like one funny thing that we noticed is when you look at the word gift, a very well simple word like gift, which means giving a present. In Norwegian language, gift means that you are married, and it can also mean that you poison. So you see the variants over here. You have present and you have marriage or poison. So that's why understanding those cultural differences is quite critical for for the AI model to understand the sentiment behind it. Now, the most biggest challenge that we have seen over multiple research papers that we have studied is the lack of high quality and large scale database. That is another thing that leads to any of the AI models not being able to grasp the sentiment behind a particular text.
So now that we've talked about sentiment analysis in general, let's get into our actual project. So one very important contribution to the sentiment analysis research space is the Go Emotions project, specifically for a lot of the reasons that Mana said, that having the large data set available. So what is Go Emotions specifically? So Go Emotions is the largest human annotated data set containing natural human text that is labeled with the associated emotion categories. And the categories that are included in Go Emotions are listed over here off to the right. So specifically, this data set is made up of approximately 211,000 entries that were scraped from Reddit. And then the researchers then had multiple people independently rate 58,000 of those entries. So then the team used those rated entries to train their original BERT-based model for sentiment analysis purposes. So our project, we took that data set and the model code that was developed by the original research team, and we aim to improve upon their work, specifically by using a novel deep learning architecture. Next slide. So the original Go Emotions project was built entirely using a BERT model. And BERT uses a transformer encoder-based architecture. BERT itself specifically stands for bidirectional encoder representations from transformers. And anyway, so BERT is now widely used as a tool for nearly every problem encountered in the natural language processing space. It's just very versatile for that sort of tasking. So for our project, we decided that we wanted to upgrade the architecture used in the original project to a hybrid multi-input single output structure. So as opposed to the original that exclusively used BERT, we are combining BERT with another type of deep learning to hopefully benefit from the pros of each architecture style. So the diagram you see here off to the bottom left, that shows the intended architecture that we described in our proposal document. So you can see on the BERT side, instead of the version they used, we decided to switch to a variation called DistilBERT for reasons we'll get into eventually. But essentially, this other version should retain the same capability to capture global and local patterns in the data, but run a lot faster than theirs. As for the other input, we decided we wanted to use a CNN architecture. For that, we used TextCNN. And CNN specifically allows more local context to be captured through examining n-grams, otherwise known as ordered sequences, things like letters, words, sentences, whatever. So then that diagram shows there's some layers that happen afterwards that combine the results of the BERT and CNN arms of the model. We originally proposed that as concatenate and dense layers, but we will talk about what we actually ended up doing later. So next slide. So why did we decide to replace the BERT they used? The main reason is that BERT is a very large model, and we already knew that our machines didn't have the resources to run it effectively. So we looked into some other options, ultimately settled on DistilBERT. And DistilBERT, it's exactly how it's named. It's a distilled version of BERT, which means it's a smaller version of a larger model that can simulate near equivalent results. So In this case, DistilBERT is 40% smaller than the normal BERT, but runs 60% faster. And metrics wise, just using the F1 score as an example of a metric to compare, the DistilBERT retains 97% of the normal BERT's F1 score value, showing that its actual functionality is pretty close. Next slide. So, second input. Why have a hybrid model at all, and why CNN specifically? So the main reason is we found various studies supporting the idea that a hybrid model can have superior results to just BERT alone, and CNN specifically was one regularly mentioned as a good choice. So some of the studies we reference are listed here on this slide, but we'll get to them a little later. So as for our CNN implementation, we had decided that text CNN specifically would be a good basis for this. So CNN itself was originally designed for computer vision, which makes it obviously excel in image processing tasks. But text CNN is a variant that was designed for use for text processing specifically, and since our data set is text, it seemed like the best choice to use. Next slide. So at the end of everything, the results that we would end up with is a multi-label indicator matrix over the data set that was passed in. So ultimately, the goal of the model is to take input and then assign one or many emotion labels to it that define what emotions that text expresses. So there are 27 potential emotions that could be used as labels, 28 if you count neutral as an emotion, that can be assigned as an outcome. And next slide. So I mentioned the other studies that we referenced, so we can go over those now. So first one, so the first one on the list is research on sentiment analysis of online course evaluation based on DistilBERT-CNN. So this was a very recent study done where the researchers also evaluated a BERT-CNN hybrid model, much like we did in our project. But they did theirs over a data set of online reviews of educational courses. One useful aspect of their study is that it evaluated BERT-CNN versus other hybrid architecture variants. And although it recognized some of the various strengths of the BERT-CNN combination, it did note some weaknesses it had to bad data sets, which was very helpful for us to be aware of. Another good study that we looked at was a BERT-based sentiment analysis model for depressive texts, and which was similar to the original Go emotions in that it used just BERT, but their specific use case was to identify depression. This study in particular was interesting because it noted that unbalanced data sets when doing a multi-label classification problem like sentiment analysis, the uneven data sets is a problem to be able to predict categories effectively, which it's a problem that the Go emotions data set also has. So in their case, they used data augmentation to try to resolve the problem. But in Go emotions and in our project, we used various weighting mechanisms, which fortunately was a strategy they also acknowledged as valid. So we can go to the next slide. So the last two studies referenced here also discuss hybrid architectures, but not specifically the hybrid architecture that we chose. So the first one is on Roberta LSTM, and that's just that, a study that evaluates using a variation of BERT combined with an LSTM structure to make a model that did show to have superior performance. And as for what Roberta is, it's another variant of BERT, but it's a variation trained to be more effective at predicting results at the expense of being very, very large. But anyway, their hybrid architecture did prove effective, so that would definitely be a great avenue to go down if someone wanted to continue this type of work, as long as they have the resources to be able to run it or more time to train. The last one listed is transformer-based deep learning models for the sentiment analysis of social media data. And that uses a combination of BERT and CBRNN. And CBRNN is itself a combination of CNN and bidirectional RNN. And it again just discussed the advantages of that architecture and strengths and weaknesses of others. So, next slide. So, problems and challenges. So in implementing our project, we did uncover a lot of problems and challenges, and some were ones we expected and just didn't realize the scope of them, while others we didn't predict at all. The first one was just caused by us trying to utilize the original Go emotions code. So it turns out the Go emotions code had its last meaningful code update like 4 or 5 years ago. And we originally thought it would be easy to work with because we saw that it was just using TensorFlow and we were learning about TensorFlow. But it turned out it actually used TensorFlow version 1. And not only did it use deprecated APIs from TensorFlow 1, it used completely defunct ones like estimators. So this led to a whole ordeal of trying to convert the relevant parts of their code to TensorFlow 2 and Keira's compatible code. As for TextCNN, there were some similar issues, fortunately to a much lesser extent. The TextCNN project we referenced was written in PyTorch, but overall the process of migrating to TensorFlow Keras was a lot smoother. It's a much more modern API, a lot more straightforward than whatever estimators was. So wasn't quite as bad as it could have been. Another challenge we hit that we didn't expect at all hit us very late in the project, and that was the updates that Hugging Face pushed out recently. So the pre-trained DistilBERT model that we implemented gets pulled from Hugging Face directly, and originally our code was regularly pulling it from their servers. But however, late last week, after we thought our code was pretty close to being finalized, Hugging Face pushed an update that changed the formula they use for model weights, the structure, the formula, and that unexpectedly broke our code. So to fix it, we ultimately had to pull the newly released version of the Safe Tensors library, but it caused some stress, and we also needed to alter our code to download and store the pre-trained DistilBERT model instead of re-downloading it constantly to help mitigate this from happening again. Next slide. So last challenge is one that we predicted. So we did know ahead of time that we would have some issues with our system limitations, and we thought we could resolve it by switching to a smaller BERT model, and that was the DistilBERT. However, that did turn out to not be enough. It still took too much time to train the model. So ultimately, we ended up migrating to the project to a Jupyter notebook and running it in a cloud environment to get around our resource limitations and sped things up a lot because we could actually use a GPU. Next slide. So next topic. Let's talk about the procedures that were used for data collection. So as mentioned, the data set for our project was sourced from the data set collected by the Go Emotions team, which was a collaboration between Stanford Linguistics and Google Research. So as mentioned before, the data set contains 58,000 Reddit comments, all labeled with one or more emotions that those comments express. So for the comments themselves, they tried to source those comments from like a specific subselection of subreddits, which they chose based on a variety of factors. One was popularity of the subreddit, obviously. However, they also tried to choose subreddits based on subreddits that showed a variety of emotions. They wanted to make sure they could see different types of emotions in the data versus overall one type of emotion, all positive, all negative, or even no emotion at all. Um, and they also tried to exclude subreddits that were known to contain a lot of offensive or harmful content. So once the comments were collected, they then had 3 raters out of their group of 82 raters independently categorize them by different emotions. And if the 3 raters didn't agree, they would just add more raters to the problem. So the table to the right summarizes the overall results of their data collection. You can see it shows like how many labels got assigned to each comment. So you can see about 83% are assigned a single label, the rest have more. There's some comments that were marked as difficult to label and how much the raters agreed with each other, so on, so forth. So next slide. So once they had all this, they then had to do some cleanup on the data. So although they tried to select for subreddits that in general didn't have offensive or harmful content, they still had to filter some of those examples out of their collected data set. But they did keep some of the profanity to help train their negative emotion set. And they also ended up removing and filtering out text that did show that the raters did say were too ambiguous for them to categorize. And lastly, Reddit comments naturally have different lengths. So they had to do some regularization to get the token length to be more consistent between comments. So on the right here, you'll see a graph. So another problem they encountered was the unevenness of the emotion categories. And this graph shows how uneven those categories are. As you can see on the right, they had nearly 17,500 examples of approval and admiration, but very few pride, relief, and grief examples in comparison on the other end of the chart. So you can go to the next slide. So they attempted to handle those uneven categories through sentiment relationships, since again, they still ended up with an uneven number of examples in each category, even though they tried to select for a better emotion spread in their data collection process. So in the original project, the team used a weights and bias algorithm to allow for rarer emotions to learn from other emotions in a similar category. So to do this, they organized all 27 motions in the higher level categories, which you can see in the table at the bottom. So things like amusement and excitement are positive, and fear and nervousness are negative, and realization and surprise are ambiguous emotions. So because of this grouping, the model can extract info and train from those models. Additionally, something we added an additional weighted loss functionality in the custom loss function we already had to further penalize misclassification in minor classes, specifically based on the emotion distribution we found, which Manas will talk about here more shortly. But first, next slide. So another mechanism that was used to add weights was how emotions correlated with other specific emotions outside of the positive negative groupings. So while the original Go Emotions project did utilize this mechanism, the code they used actually wasn't available to us. It doesn't seem to be included. So we ended up recreating the general idea of what they were doing based on their description. So the overall purpose was to show where emotions tend to be expressed together, and therefore showing a different type of relationship the model can learn from, especially in the cases of rare emotion categories again. So next slide. So this is the emotion correlation matrix we generated, and it is certainly difficult to read on the slide here, but this matrix does show the calculated relationships between each of the various emotion categories. Some highlights I did want to point out here. For our highest correlation values, we have the following. We have nervousness and fear with the highest correlation at 0.2, which makes a lot of sense. And behind that, we have joy and excitement correlating at about 0.1. And close behind those, we have anger and annoyance at 0.09 and disappointment and sadness also at 0.09. And all of these are completely logical to have as correlation emotions. So seems right. And next slide.
All right. So now that we have discussed about what are the different data pre-processing steps which are used, like sentiment grouping as well as correlation metrics, let's look at what are the different custom functions that were used using those values. So some of the custom functions that we use, the reasons for using that was primarily to the balance the data imbalance that we have, and also it helps in fine-tuning the overall model as well. The first function that I'd like to talk about is the custom loss function. And what it does is it, apart from just calculating the difference between the predicted value and the actual value within the test data set, it incorporates some regularization as well. So first we calculate the base loss. And on top of it, because we have a huge data imbalance, as you could see that we had 17,000 in one and a few hundred in, let's say, grief or relief, it adds a weighted loss function on top of it. How a weighted loss function is added is it looks at the overall distribution of the emotions, and based on the distribution it penalizes any kind of loss in the minority classes. So anything which has less number of data examples, and if you see a loss by the model, it will penalize the model more. So that way it is able to add a weighted loss function on top of it to regularize that. On top of it, it will also add a sentiment regularization, and what it does is if the model predicts uh, two emotions which belong to two different sentiment groups, then the model penalizes the loss function penalizes the model more. And on top of it, if you have we also added a correlation regularization, and what it does is similar to sentiment regularization. If totally correlated emotions are being predicted by the model, then the loss function is going to penalize it more. On top of it, we added activation functions on top of, based on the whether we are trying to find a multi-level emotions or a single level emotions. Now, for multi-level, we use sigmoid activation functions so that we are able to detect more than one emotions. And if we were planning to use a single label and we wanted to find out the best emotion for a particular text, then we can use a softmax activation function as well. So that is how those activation functions are decided within this custom loss function. The the next custom function was the custom learning rate function. We used the AdamW optimizer over here, and what it does is this custom learning rate function. It has a two-stage learning rate schedule. We started off with a few warm-up steps, which is around 10% of the overall runs. And what it does, it moves the learning rate from 0 to the desired learning rate, which is 5e minus 5 for us. And once it reaches that level within the 10% of the steps, then the remaining 90% of the steps, it is going to gradually decay the learning rate, ultimately reaching 0 by the end of the overall learning step. Then we also had a custom classifier function, and this classifier function is used in place of the Keras dense layer. What it does is it predicts the emotion using custom weights and biases that we discussed earlier. And lastly, we also had a custom metrics function. Uh, I mean, we do have the Keras metrics F1 score, but that is the standard F1 metrics are better for single label problems, whereas we had a very data imbalanced problem and we were trying to measure multiple labels out of it. So in case of a multi-label class imbalance cases, it's better to have a weighted F1 score metric. So this custom metric function is used in place of the standard F1 metrics to find out our overall F1 score. Okay, now moving on, this is the final, this just a overview of what the overall network architecture was. So as you can see, we have two inputs going over here. You have a text CNN layer and you have the BERT layer on over here. On the BERT layer, you have an attention mask, which will help the TF DistilBERT understand which are the areas within the text that it needs to analyze without focusing on the padding, because as we are trying to keep the overall sequence length same, so if some texts are quite small, we have added padding on top of it. So this attention mask is going to help the DistilBERT to understand which areas are the padded areas, so that it doesn't focus on those at all. That saves time and the computation time as well. So once that attention marks and the input layer goes to the TF DistilBERT, it goes through the processing. It tries to understand the most important features within that particular text, and after that, it assigns emotion for that, which we are trying to slice it to the slicing of umbrella layer. This slicing of umbrella layer is going to fetch the first token within the overall list of tokens, and that will have the summary of what the emotion within that text is. On the left hand side, you see the text CNN layer, which what it does is the input goes into the embedding layer first, where it gets tokenized. Once it is tokenized into a different integer values, it is passed through multiple filters. This filter sizes will be different. And once those filter sizes it passes through them, it goes through max pooling to fetch the most important feature out of it. And after it fetching the most important feature, it concatenates all of that to find out a common feature within the complete text. So as we have different filters, it finds out the common filter out of it, which is then sent through a dropout layer for regularization. And once that is done, we combine both of these so that we can have the information from the text CNN layer, which is going to give us the local context, and we'll have the global context from the TF DistilBERT layer. Once we have the global as well as the local context, we concatenate that together, which we pass it through a dropout layer for regularization to prevent any overfitting, and finally through the custom classifier so that we can find out what exactly is the emotion that the model is able to predict. So that is, and finally the output from the custom classifier would be a multi-level emotion matrix. This is some more details around that, talking about what exactly each of those layers does. And as I was talking about TF DistilBERT, as you can see, it first tokenizes the text and uses the attention vector to find out what exactly is the real content. The TF DistilBERT is going to use the self-attention mechanism to find out the importance of each word and understand the global context behind it. And the slicing of lambda layer is going to extract the embedding of the first token, which will be the summary of the overall text. Okay. Over here, as I already discussed about how the filters are used to capture the local patterns, and that's exactly the whole function behind the n-grams. You have trigram, you have diagrams, and so you have two layers of two filters. You have filter sets of 3, filter sets of 4, filter sets of 5, and through that you're getting different context of the different sections of the word together to come up with the essence of what exactly the local essence of the text. Okay. Moving on, this is the combined layer, which we discussed how the output layer of the local context and the global context is combined to form into a single vector. We use the regularization layers to prevent any overfitting, and finally through the custom classifier. And this is an image of the actual model. As you can see, this is pretty complex, so we try to create a simpler version in the previous slide so that it is easier for everyone to understand. We could see that the overall number of parameters was over 690,000 parameters that got generated. 690, actually it is 69 million parameters that got generated out of the model. Now, for our overall network training, we had the 58,000 records, and that got split into train, validation, and test. So we broke it down into 80% of training, 10% of validation, and 10% of test records. Additionally, we also added some configurations in our overall model run, which was just like the original research project. We used the batch size of 16. We kept the initial learning rate as 5e to the power of -5, and we had a warm up of 10% of the steps as well. We had a epoch of 20 epochs. We thought that maybe we'll try to train the model more. But on top of it, we could see that the model, when we ran it for multiple times, it was getting overfitted. So we started adding an early stopping mechanism on top of it. So that we added a 3 epoch early stopping, so that if the model is not able to learn anything new within 3 epochs, it should stop running. and that way we kind of prevented any kind of overfitting in the final result. So even though 20 was the epoch count that we started off with, the actual number of epochs that it actually ran was 6 usually. Now, here are some of the outcomes that we found out. As you can see, here is the list of different emotions on the left-hand side with the precision, recall, and F1 score. The reason why we did not focus on accuracy so much was because in case of imbalanced data sets, accuracy doesn't give us much information. And when you're looking at sentiments, the precision in which a particular model is able to understand an emotion or the recall of it are more important. And F1 score is the most important metric for imbalanced data sets to help us understand which model actually is able to work better or not. So here is the breakdown of the different F1 scores for different emotions. And on the right hand side, you could see that the per class precision, recall, and F1 score for each of these emotions over here. Some of these you could see that, like for gratitude, there's a huge F1 score over here, which is really high. And we could see that admiration has so gratitude over here, if I can go over here, you can see it's zero point 0.9. Okay, so you have a 0.94 precision and 0.87 of recall. So it was, the model was able to understand gratitude a lot well, as compared to relief, which had 0. So for cases of relief, it was not able to guess anything at all. Moving on, so we do have we also created some confusion metrics as well. So I'll just try to run that video on site while I talk about it. So this confusion matrix was created, and through that we could also gather the precision, recall, and F1 scores. What we observed is that the metrics that we saw for this confusion matrix was not related to the frequency of the data available, because in cases like if the data was really small, like in case of grief, still we could see that it was able to predict it quite well, and the F1 score was decent enough. Whereas in case of somewhere around here, like disappointment, which has a really high number of count as compared to grief, still the scores were quite low. Now, we also could see that the metrics was not related to the sentiment groupings as well. We thought that maybe positive and negative sentiments are so polarized that that it will be able to understand and able to grasp those. But we did not see that that is the case, because some of those ambiguous examples as well, like relation, it was able to understand that and it was able to guess them properly. So that did not help us in understanding or figuring out a pattern between this, to focus that okay, maybe the data is the culprit over here, or if the sentiment grouping being ambiguous is the culprit, where in cases where the F1 score was low. Moving on, some of the other key findings that we could see is that this is the accumulation of all the summary that we have tried to see, that gratitude, love, amusement, grief, these were the top rated emotions that the model could predict. Whereas embarrassment, excitement, nervousness, relation, and relief, as I already discussed, which had a 0 F1 score, were some of the worst performing emotions. We could also see that in case of low data support, like in case of nervousness, embarrassment, and relief, where we had really low data, that could be one of the cases why we have really low F1 scores for those. And that is one of the possibilities that we think. And maybe in the future, if we are able to label more data and get more data in those categories, maybe the model might perform better. Now, in some cases, like case of curiosity, we could see that it had a high recall but lower precision. That means the model was actually casting a wider net in this case, and it was getting a lot of true data. Whereas in case of disappointment, it was a high precision but low recall. That means the model was very precise about it. It was casting a lower net, and it was able to get only lower amount of positive data, whereas it was missing out a lot of positive actual disappointment cases too. In case of neutral emotion, we could see that it has a moderate F1 score and it has a lot of false negatives. And that's why we can understand that the model is not able to identify all the neutral instances right now. So yeah, a lot of work needs to be done in case of neutral category for sure. Now, this is our comparison between what was done by the Google research team that we already discussed. So this is their snapshot of their scores, and you could see that this is their macro average. This is the 0.40 of their precision. 0.63 was their recall. That means they had a good recall. and the F1 score was zero point 0.6. Our macro average was 0.62 from precision perspective, 0.43 from recall, and 0.48 was the overall F1 score. So as we discussed earlier, that F1 score is the most important metrics in case of imbalanced data sets, and we could see that we were able to beat the original 0.46 metrics that was the target that we had set out with. So we were able to make an improvement over the F1 score, and we could see that we had a better precision, but we had a lower recall in the overall score. Now we also tried to do some research to understand what does that mean, and what we could find out is that in case of AI therapy or customer service chatbots, those kind of cases, what industry prefers is a model with higher precision score than recall scores, because they want people who, if there is a customer issues, or if the particular issue is that needs to be highlighted and that needs to be sent over to the right team instantly. So that's why the industry prefers a higher precision score in these cases. And because in our model has a higher precision score and a higher F1 score as compared to the original Google research, and our aim has been to create this model for AI therapy. So that's why we consider that as a win overall for us. Now here is a run of a demo for the overall model. I'll just play it around, and I'll try to stop in between when we see something important. So this is the overall summary of the model. This is how our model was running. So I'll just move it back. As you can see, it was trying to run it stopped running at 6 epoch. So when it could not see that there is an improvement. And we tried to create some Jakarta scores as well. I know Jakarta score was not that important. Jakarta score is primarily used for CNN models to understand the integration over the union. But we try to gather some Jakarta scores and understand how often the model is able to understand the predicted labels better. This is the overall classification report which we shared, and as you can see, it has a 0.48 of F1 score. And this is the complete classification metrics of all the 28 emotions. And this is to just try to gather all this information to understand which of the emotions are better handled and which of the emotions are not handled that well. So that is, as you could see, we have this as the top emotions and this as the worst performing emotions. So yeah, that was our overall demo for this. Now let's move on to the lessons learned.
Yeah, so what did we learn from this other than what we learned from the model results specifically? So, first thing I'd say, we learned that reusing existing project code is actually a lot of work. And frankly, it was probably more work than just writing our own model from scratch on top of the existing data set. So, yeah, as I mentioned before in the challenges section, the Go Emotions code hasn't had any meaningful updates for at least 4 years, and dealing with their extremely outdated models and dependency on deprecated and completely removed APIs was a huge pain. So that did lead to the frustrating choice of one, we could pin our code to use the same extremely outdated models, but then we'd be losing access to new developments in the AI space, and not be able to take advantage of the TensorFlow and the Keras stuff we were learning in class. And so learning to use outdated APIs just seemed like a waste. So yeah, that's why we ultimately ended up upgrading and refactoring the code. May have been better off just starting from scratch. Another complication with with using the Go Emotions project that I didn't mention earlier was some incompatibilities in how it was expecting to run. So specifically, their project was designed to run from a Linux bash command line, and we have Windows. So sure, it would have been possible to get it running through something like Windows Subsystem for Linux or a bash emulator, but since we wanted it to be easy for us both to run and to share the code, we ultimately just migrated everything from the command line to Jupyter Notebook to get rid of a lot of the issues that would have been caused by just trying to get the thing set up to run in the first place. Um, Third thing, listed here was also mentioned in our challenges slide. We learned we needed to cache everything locally, not just the modules we're using and so forth in our data sets, but also the remote models, because of the whole Hugging Face issue I mentioned earlier and how it broke the compatibility with the Python modules we had already used and the code we wrote and had to do some updates. Next slide.
All right. Some of the other lessons that we learned was that running the BERT model was very process intensive and time consuming. So we also tried to run it locally as well through the non-Hugging Face pre-trained model. And when we ran it on our computers using our system resources, it took 4 hours per run. The overall run it took. So each of the epochs it used to take 1 hour to complete. Um, Now, that was one of the challenges. So we had to move over to something on a cloud environment and pay for the GPU compute to get it done. Now, another thing that we also observed is that the multi-level classification on this uneven data sets is very complicated. We had to go through a lot of trial and errors. We had to go through a lot of research papers, understand what they are talking about, what are the challenges that they have faced, and how we can fine tune it. So yeah, that was a lot of challenge, but ultimately it still helped us learn a lot of new things as well. Um, on top of it, it feels, I mean, we have to also understand and also observed is that after you train the model using GPU compute, it is better to just download the model file and use it locally to, let's say, play around with the test data set or different test data sets rather than using the GPU compute and wasting some time over there. Maybe just download the whole model file and run it locally. That way, you are able to understand the results, understand and interpret the results better. So that is another thing that we kind of understood. So our recommendation is that maybe when you're trying to create a new model, train it using cloud, but then download the whole model file and use it to for any kind of data interpretation and running the test set on that. The last thing that I would like to mention over here is that the sentiment analysis, it needs humongous amount of data. We discussed about using their labeled data set, which was one of the largest and human annotated data set. And still they had some things which were unclear. Still they had many of the items which they did not even label or thought that it is not that clear to label. There are a lot of challenges and a lot of things that you could actually do to solve those data imbalance or lack of data. We could say, while we use the weighted loss function for regularizing those kind of data imbalances, there are other options available as well. Like you could augment the data, you could add more labels, you could spend time in maybe acting as a rater and try to label those different items which are not yet rated. We could also do some oversampling of the minority classes or undersample the majority classes as well, and all of this was possible. We did not go through that route. We went through the algorithmic route of creating the weighted loss function. But if anyone wants to just improve upon this work and wants to use it, they could try those other options as well. Now, ultimately, as we discussed, like some of the stuff we try to reuse the code, maybe we should have, in hindsight, we feel that maybe we should have invested more time in processing the data more and more. Any kind of inconsistencies in the data that we see, maybe we should have spent more time over there. And maybe once we have a much more accurate and labeled data, we could use some of the standard functions as well to possibly get a better result. So yeah, if somebody wants to just try it out on the same data set, they can invest more time in the data processing aspects of it, create a much better data than what the original researchers have created, and then work upon it and see if the results actually help. Okay, the next is all the different bibliographical references that we have focused on. These are different papers that we went through. Then this the data set and the source code for both GoEmotions and text CNNs we referenced to see how we can fine tune and then utilize in our model. Then these are some of the websites that we also use to understand more about the metrics and see how those metrics actually help in real life industry scenarios. Some of the website also provided us with the images that we have used in this presentation as well, like categorizing those into different buckets and putting those emojis. That kind of like felt like a really nice picture to have. So we kind of used it from one of the websites as well, which is this one. All right. So that's pretty much our presentation. And thank you all for being part of this journey and listening to us.
Thank you.